All right, you're welcome back again. We want to continue from where we stopped last time. We're still looking at unsupervised learning, looking at the principal component analysis under dimensionality reduction. So we have looked at clustering, I've looked at association, I've looked at now we're looking at dimensionality reduction. This dimensionality reduction is the third one of third category of our unsupervised learning algorithms that we have mentioned thus far. All right. So under it, we have some other algorithm under it, which we look at few of them before we move further. And the principal component analysis happen to be the top notch among those ones because it's generally used in almost now every disciplines. Okay, so it's a popular unsupervised dimensionality reduction technique in machine learning that used to transform high dimensional data into a lower dimensional representation. It's used to identify patterns and structures in data by discovering the underlying relationships between variables. It is commonly used in the application such as image processing, data compression, and data visualization. Now, it works by identifying the principal components of the data of the PCs. We have PCs, PC1, PC2, PC3, and so on, which are linear combinations of the original variables that capture the most variation in the data. So the first principal component accounts for the most variance in the data, followed by the second PC or principal component, and followed by the third, and so on. So by reducing the dimensionality of the data to only the most significant pieces, PCA can simplify the problem and improve the computational efficiency of downstream machine learning algorithms. So we have some selection of PCs, all right, from PC1 to the number of PCs that we have there, and which we may select by percentage because they are not all the same PC that they have a good distance. So PC1 have the highest variation, followed by PC2, and followed by PC3, and so on. So and there are steps involved in PC. We have to standardize the data first. It requires that the data is standardized to have zero mean and unit variance, and then you want to compute the covariance matrix, which you compute the covariance matrix of the standardized data, and also compute the eigenvectors and eigenvalues of the variance matrix. PCA then compute the eigenvectors and eigenvalue of the variance matrix. We select the principal components based on their corresponding eigenvalues, which indicates the amount of variation in data explained by each component. So we got that to eigenvalues. So PCA also projects the data onto the new feature space defined by the selected principal components. So are just basic steps that we go through in implementing PC. So this is done automatically behind the scene mathematically. All right. So we are going to look at implementation using our data set we have used several times before called ERIS, which is a popular data set you can get online. So we run this line of code and then import our libraries and then run our data set. Look at the structure first. You can see it here. So we also we standardize the data. I call our standard scalar. So you can see based on the mean and STD. Right. So we also apply our PCA now to it. We call our PCA components now. So we select only two components for now, which is a first and second columns. All right. So if you want few more of the visual principal components of the each dimensions, you can select more than 2, 3, or 4. So I can see maybe you want to try to pair principal components 1 and 2, or 1 and 3, 1 and 4, 2 and 2, 2 and 3. I mean 1 and 2, 2 and 3, 2 and 4, like that. You want to pair them. You can do that easily using by adding more components here. All right. So the one we are using so far is 1 and 2. This one is 2. All right. That is by default. We will select 1 and 2 only. So to fill the so here we have in a PC explain now. We have 73 approximately percent is explained by PC1, while 23 approximately is explained by PC2. All right, so you can see here, so we have 0.729 and 0.229 for PC1, PC2. So look at what we have explained. That's number of pieces that to combine together. Now we know what we have together. So we can visualize the result here, right? So when you run this, we have result visualize here. You can see here our PC data set, data set. So this is our result of user component scatter plot. Right. So we also understand that the PC1 separate Sentosa as left from the face color and vagina right. As you can see here. So Sentosa is here. Here's a left here, and face color and vagina is right here. Also, we also know that the PC2 partially separate face color middle and vagina top right. So you can see here. So that's the PC1, PC2. All right. So that is so now we can interpret the principal component actually by looking at each of the PC and under PC loadings. So you can see each of the PC you have here. So you can have when you have the main data set, you can have a lot of PC like that. So we have PC1, PC2. So PC1 is dominated by beta, so sepal, right, with all positive weights. You can see them, all positive weights. We are looking at our loading. Now, the loading means the weight, okay? That's means the loading. We have PC2 is strongly influenced by SEPA with negative weight, right? That is a PC2, right? It's strongly influenced by SEPA with, right? So you can see negative is minus 0.269 there. So now we can look at our screen plot here. This our PC has been scaled now, transformed, right? So you can look at the screen plot. You also want to add some number, I mean some percentage acquire on the each of the bar so that you can see. That's why we do I do this to add value to the top of the bar. So that's what I do on normal ratio code. So we have our PC explain here. This is the cumulative explain variance is in red form, like if I explain, you have this one, like this. This is our script plot. You can see the bars. So here we have 73% explained by the PC1, this PC2, PC3, PC4. All right, so that's what we have. And the key insight here is basically first two pieces are captured approximately 95.8% when you combine together to two variants. Okay, of course, when you see at the PC1, 73%, and this one 3%, so you can have approximately close to this. So you can reduce 4D data to 2D with minimum information loss using principal component analysis. And what does it do actually? It centers the data, which is surprising me. It rotates axes to align with directions of maximum variance, which is called principal component. And it orders PCs by variance explained. PC1 is more than PC2, and so on. So the lower the PC number, the higher the PC value. So we have or PC explain rather. So component rules of thumb is that keep PC that explain more than 80% to 90% cumulative frequency. All right, that's what we have to keep to use. So there are always very few, maybe few pieces, depending on how big your data set is, okay, or the column, right, the number of variables you have rather in your list. So we also have a script plot. So we look for the hebo points. All right, like the one we saw here now. You can use hebo. So it's hebo 1, 2, can if it's 1 PC2. So that is a hebo we can choose. And when we use PC, we reduce 4D release data to 2D or 3D. We remove low variance components. That's a noise reduction. And they also have handle what is called correlated features integration. That's multi-collinearity. It also handles preprocessing for machine learning models, which is called dimensionality reduction for future purposes. So we want to generate our features for machine learning. So we use that dimensionality reduction for it. So I'm going to look at more later as we journey gradually under this series. So for now, this is just a basic thing that we understand now. So we do more as we journey gradually in this particular training. So thanks so much for listening. I will see you in the next class. Bye for now.